Hello, everybody. My name is Kyle Shorey, and this is my lab report numero Cinco. So I'll go over the lab. I'll introduce the lab, go over what the procedure, go over the model, data analysis, some of the errors, and then what if and what it means. So to start off, I ended up going with the Slinky lab, and the purpose of the lab is to compare the two different motions from the top of the Slinky and the bottom of the Slinky when it's dropped with their experimental models. The main physics principles used are the second law, which centers around relating forces, and how external forces acting upon a system will change the momentum, resulting in a corresponding change in velocity. In performing this experiment, we're aiming to use the data to verify the accuracy of Newton's second law and explore the idea of net forces as well as gravitation. So, preview of the main results. The top of the Slinky ended up moving down immediately when it was dropped, while the bottom of the Slinky remained still until they collided. Some of the equations I used: position update formula, which uses Newton's second law, position update formula, and F net, which is just F equals ma. So the procedure, to start off, use a video on YouTube to get the full motion of both the top and the bottom of the Slinky, put it into Tracker. I track the motion of both of them as separate masses, and I used point tracking for that. And then once I got a data set, I copied and pasted it into Excel, and then I was able to compare that with glow script code that I used to make models. And yeah, for that one, we basically just set the initial conditions, started editing some of the variables using physics equations to set up each one, and then ran it and got our results, and then we were able to compare. Some of the assumptions I made while running this experiment are that the only forces acting upon the Slinky system is gravity, therefore we didn't account for wind or drag, and then we assumed that the tracker placements on the parts were consistent throughout the entire tracking. Some initial conditions are obviously the system of is the Slinky, and the surroundings is gravity and the hand that released it. Initial actual initial conditions, we have initial height was 1.7, initial for the top, the initial height for the bottom was 0.51. The mass for both parts, we just made 1 kilogram. Gravitational constant, delta t, and t. You can see there. Here is how I used the velocity update and position update formulas for both the top and the bottom. You can see I have two different versions for it. And then for FNet, I was able to use it in the velocity equation. So for our initial conditions here on the left, you can see all the initial conditions. When I was making the code, we also had to create a couple new objects. So we have two balls that are being tracked, which each represents a different part of the Slinky. And yeah, on the right is the iteration through the loop, which can be seen here. Same thing that I did for the top, I did for the bottom one in terms of tracking the position, velocity, using up position and velocity update formulas. But you can see I have an if loop inside of the while loop for the motion of the second part of the ball, because this takes place after the collision at 0.3 seconds in my data. So here you can see the glow script results versus the tracker results. Pretty similar, especially for the bottom part of the Slinky. You can see how it stays still at the very beginning, and then once after the collision, it has the same velocity as the top part, which started at that velocity immediately after it was dropped. And yeah. Then potential errors and improvements. There were potential errors in placing our points on tracker, potential error from not accounting for wind or drag, and then potential error for rounding errors, just doing the math. So what does it mean and what if? Why does the bottom of the Slinky stay still to begin? The reason that it stays still is because the net force acting upon the bottom part is 0 until it collides with the upper part, of course. Acting down on the bottom is gravity. Acting up on it is tension. Because they cancel out, it leaves the net force 0, and we know that the initial velocity is also 0, so therefore it's just going to stay stationary. What if the Slinky continued to be tracked? We know that after the collision, they move down together. So it would continue moving down together as a full system at the same velocity with constant acceleration. Once they hit the ground, we would expect it to bounce up again due to the transfer of momentum once it hits the floor. But yeah, that's all I have. Thank you for watching.